Hello and welcome to TJC Physics. In this video, we're going to look at an aspect of solving inclined plane problems.
In introductory physics courses, students learn how to solve problems using Newton's second law. This usually requires you to do a free body diagram showing all the external forces acting on a system or an object, and we usually find the components of these forces along coordinate system, x and y axes.
Confusion can sometimes start when we're doing inclined plane problems and have to rotate these axes.
And the geometry and which angles to use and how to find the components can be somewhat complicated. An example of an inclined plane problem might be something like a snowboarder sliding down a snowy hill with an incline of theta. Now, we've seen in class that solving any type of Newton's second law problem involving situations usually involves a free body diagram with a coordinate system. Now, we generally try and put one of the axes of the coordinate system along the direction the object moves. It just simplifies things later down the line. So in my example here, even though I'm not giving you a specific question, I've drawn the x and the y axis and they're tilted. Now we'll be able to draw a free body diagram and put the forces on. There's the gravitational force acting on the snowboarder, which would go straight down, be equal to m times g. There's going to be the normal force, which points perpendicular to the surfaces in contact. And even though it's a snowboarder on snow, there is going to be a bit of friction. That'll be a kinetic friction force pointing up along the x-axis. Now, with these three forces and knowing the angle of incline, we can go ahead finding the components of these forces along the x and y axes. Now, finding the components of the normal force is easy, because the normal force is only pointing along the positive y-axis. So in terms of our vector notation, we could write it as 0 I hat plus Fn j hat. Similarly, the friction force only has a component along the positive x-axis. So we would write it as Ffk I hat plus 0 j hat. We didn't have to do any trigonometry to find components for Fn or Fk. However, the components of the gravitational force won't be as easy. We're going to have to do some trigonometry. I'll quickly just sketch in these vectors. The x component will point along the negative x-axis in this problem, and the y component will point along the negative y-axis in this component. And I'll label them FGY and FGX. And I'll quickly put those symbols back into my overall FG on the I hats and j hats, just to make it a little clearer. When I sketch it in, you can see we are dealing with a right triangle. But in order to use trigonometry, we're going to need to find one of the other angles inside that right triangle. And that's where we're going to have to look at some of the geometry of it. To make the geometry a little clearer, let me redraw my x and y axes on an incline and show the angle theta. Now I'm going to drop a straight vertical line in the same direction as FG, straight down, and draw a little right triangle in blue, connecting those two. So in this right triangle I've drawn, we know one of the internal angles is theta, we know one of them is a right angle, 90 degrees, and we'll call the other internal angle phi. So one of the most well-known rules in geometry is that for a triangle, all the interior angles must add up to 180 degrees. So theta plus phi plus 90 has to equal 180. So theta plus phi would have to equal 90. And phi would turn out to be 90 minus theta, which I can replace in the diagram. Now let me clean this up and get rid of that right triangle, but leave the positioning of 90 minus theta where it is. Now let me draw a second right triangle. You'll notice this one actually matches the shape of the one we did in our free body diagram. So we know that the angle between the axes x and y is 90 degrees. I've indicated a little right triangle sign there at the origin. And I'm going to define that interior angle right by the 90 minus theta to be called alpha. Now notice in that region, if we take our 90 minus theta and add alpha, that needs to add up to the 90 degrees between the x and y axis. To write that as an equation, you'll see that we have alpha plus 90 degrees minus theta has to equal 90 degrees. We can then simplify that down to alpha minus theta equals 0. This shows that alpha is actually equal to theta, the angle of the incline. So to clean it up a bit, you can see that the angle of incline is equal to the interior angle shown on my right triangle. This matches up to the right triangle on a free body diagram. So now that we know the angle, we can now go and determine our FG components. Specifically, you can see FGX represents the opposite side of that right triangle right now. It'll be represented by a sine function. Specifically, FG will equal negative mg sine theta. Remember, we put in the negative sign because you can notice here that the FGX points in the negative x direction. So I'll take it and write it up in my list of components as negative FG sine theta I hat. You can also see that FGY represents the adjacent side of the right triangle, so it can be represented by a cosine function. Specifically, FGY will equal negative FG cosine theta. And the negative sign again, because that component is pointing in the negative y direction. I'll write it up in my components so that now the j hat component is negative FG cosine theta. At this point, you can just carry on solving the problem. But it's good to note that no matter what angle they give you for the incline or how they define it, using a little bit of simple geometry, you can figure out how to use that angle to help find components of forces. And that brings us to the end of the video. I hope you found it helpful, and thanks for watching.